Okay, so I hope you enjoyed that video of Landon the Rocket Man. And now we're just going to do a few follow-up questions just to solidify some of our learning. So the first question we have here is they're asking us to draw free body diagrams showing the forces acting on Landon in three situations. Before he fires the rocket, during the rocket firing, and then after when he's still moving but the rocket has stopped firing. So we've got our three situations here. We'll start off with our first one. Let's just label that A. Now, you'll have to excuse my artistic ability or lack thereof. I'm going to represent Landon and the rocket cart as a box with wheels. As you can see, this is pretty much the limit of my personal artistic abilities. So when Landon first gets on the rocket cart, he's just sort of sitting there in place, and he's not moving. He's just sort of waiting for the launch. Now he is standing, or sitting rather, on the surface of the Earth, so we know that there's a force of gravity pulling down on him, but he's not falling through the ground. He's not accelerating through to the center of the Earth, so there must be some sort of force upwards balancing him, and we know from what we've learned in class that we call this Fn, which is the normal force that's supporting him. Now the thing we know about these two forces is that they are absolutely, certainly equal. He's not accelerating at all, and so there are no unbalanced forces acting on him. Now, it might be tempting at this point to ask what's happening with friction. Well, since he's not actually moving, then we're not going to really concern ourselves with friction here. However, in the second case, once he starts to fire the rocket, we'll see that that's a different case. All right, let's make a little room here. All right, so once he starts to fire the rocket, what happens? What changes? Again, you'll have to excuse my artistic abilities. The same forces that we had before are still acting on him. We've got gravity pulling down, and we've got a normal force pushing up, supporting. And again, those two forces are going to remain absolutely equal. What changes is now we've got an applied force, and the applied force comes from the rocket thrusting Landon forward. That applied force is, of course, due to Newton's third law, which says that every action force has an equal and opposite reaction force. So when the gas is pushed back out of the rocket, then Landon is pushed forward. Now, because he's moving, we're going to draw our friction force, and remember, for our purposes, friction forces are always working against motion. You'll see that the applied force here is much, much larger than the friction force, and so he's accelerating forward because it's an unbalanced net force in the forward direction. All right. Last but not least, Landon, as he sort of coasts, pardon me, as he sort of coasts to a stop. All right. Whoops. Just, pardon me. All right. So, once he stops firing the rocket, now Landon's still moving. And he's still rolling forwards. And of course, he's still on Earth, so there's still gravity that he needs to worry about. Gravity upwards, and gravity downwards, and normal force upwards. There's a friction force, the same friction force that was acting on him the whole time he was moving, and that's it. He's still moving forward, but there's no force pushing him forward. He's just moving under his own inertia. Now, I guess given enough space, he would eventually roll to a stop, but of course, as we know, he had to roll to a stop with the help of Kieran and Sean, who managed to jump in the way and stop him from hitting the wall. Okay. Moving on to the next question. Now, this is going to involve a little bit of calculation, a couple of formulas. So Landon and the rocket cart have a combined mass of 95 kilograms, and he reaches a top speed of 8.6 meters over a distance of, 8.6 meters per second over the distance of 10 meters. If there is 5 newtons of friction force acting on him, what is the applied force provided by the rocket? Okay, so first things first here. We know that we're going to have to use, at some point, this is going to relate all back to Newton's second law, which says F net is equal to mass times acceleration. Now, the net force we think of as just being the winning forces minus the losing forces. So in this case, there is one winner, which is the applied force pushing them forward. And there is a losing force, or a force in the negative direction, which is the force of friction. So these two are going to equal mass times acceleration. If we want to find the applied force here, then we're going to have to figure out our other two unknowns. We know his mass. But we don't know the acceleration, and we're going to have to find that first. So, to find his acceleration, let's see what we got here. We've got a little bit of information. We know, for example, if we think of all of the variables with kinematics, we've got final, initial velocity, acceleration, displacement, and time. Let's see what we know. Well, his final top speed that he reaches is 8.6 meters per second. His acceleration, don't know. His displacement, however, is 10 meters. Now, it may seem like those are the only variables we know, but if we think of it, since Landon started off at rest, it's actually just sort of implied that his initial velocity is 0. Now remember, whenever we know any 3 of these variables, we can always solve for the other unknown. And so we're going to look to our formula here that says v squared equals v naught squared plus 2ad to solve for our acceleration. Now, just doing a little bit of algebraic wizardry, we can move this around and we get the acceleration is equal to the final velocity squared minus the initial velocity squared, all divided by 2 times the distance. And substituting in our values, we see that we get 8.6 meters per second squared minus, well, 0 squared, that's easy, all divided by 2 times the distance, which is 10 meters. Now our 0, really, we know that that's just going to cancel out. So I could have gotten rid of this sooner. I'm just going to get rid of it now to make my calculations a little bit simpler. All right. So what do we got here? Just turn this on. Okay, so we've got 8.6 squared divided by 2 times 10.0, and it looks like our acceleration is 3.698 meters per second squared. So let's write that down, 3.698 meters per second squared. Now, there's no point in rounding that off because we're still going to use that in our calculation, so we're not quite finished with it. We'll keep all those sig figs until we're totally done. I'm just going to jump back to my starting formula here. Remember, we're solving for applied force. So I'm just going to rewrite this here as applied force is going to equal mass times acceleration plus force of friction. And again, substituting in our known variables, we know that the mass of Landon and the rocket cart, just to check back up here, is 95 kilograms. His acceleration, which we found down here, 3.698. I'm just running out of room here, so I'm just going to move this over. Plus our force of friction, which is 5 newtons. Okay, now I just left that number in my calculator. My acceleration is still sitting there, which is kind of handy. So we're just going to do this all in one go. 95 times my previous answer. Now remember, as long as you remember your bed mass rules, you don't need to worry about any brackets or anything like that. And we get 356 newtons. So it looks like 356 newtons. Just going to check my sig figs. Looks like I've got 2 sig figs, lots of sig figs, and 2 sig figs. So really this should just round off to 2. So let's call it 360 newtons. Call that my final answer. Whoops. Okay, last but not least. Okay, as previously stated, the mass of Landon in the rocket cart is 95 kilograms, and he reaches a top speed of 8.6 meters per second. If 4 kilograms of carbon dioxide gas is emitted by the rocket, what is the average speed of the gas as it escapes? So we know that Landon is pushed forward by the gases that are being pushed backwards, right? That's Newton's third law, the equal and opposite forces. So let's take a look at this. Let's think of this as like a bit of a before and after picture. So here's the before picture. We've got Landon and the cart all together all in one. Okay, maybe I'll draw Landon on here this time. Really flex some artistic muscle. There we go. And he's pretty excited because he's about to blast off. Now afterwards, we've got Landon and the cart. He's still pretty excited. But now they're moving forwards. And they reach a top speed of 8.6 meters per second. The thing that you have to recognize is that's not the whole story, right? There's this cloud of gas that's kind of getting emitted from the rocket. Now that gas is also moving, and you'll notice that it's moving in the exact opposite direction. So this is the speed that we're interested in. How fast is this gas traveling? Now there's a couple of different ways we could do this, but I would kind of suggest that the simplest way is to think of this in terms of momentum. We know that our total initial momentum has to equal our total final momentum. Now this is nice and simple because in the initial case, when Landon, he's sitting there on that pile of rocket fuel, but they're not moving anywhere. And so the total initial momentum has to be 0. Now in the final case, Landon's moving forward. So I'll call this P1 for Landon's momentum, plus the gas is moving backwards, I'll call that P2 for the momentum of the gas. This is our conservation of momentum. We know that momentum is equal to mass times velocity. So this is like m1 v1, and this is m2 v2. And this whole thing has to equal 0. Well, we've got a nice simple expression here, which we can solve for v2, which remember is the speed of the gas. So v2 is going to equal negative m1 v1, all divided by m2. Put in your variables and solve. The mass of Landon and the cart, we've got right up here, 95 kilograms. We've got his speed, which was 8.6 meters per second. And then we've got the mass of the gas, which is 4.0 kilograms. Just make a little bit extra room here. All right. Now I'll put that into your calculator and solve. We've got negative 95 times 8.6 divided by 4 gives us a somewhat surprising negative 204. So negative 204 meters per second. Now a couple things about this. The first thing is that we've got to round off to appropriate sig figs, and it looks like we're only good to 2 significant digits. So we're going to have to round this off to 2 sig figs, which is a little bit annoying to do. We're going to have to do this with scientific notation. So negative 2.0 times 10 to the 2 meters per second. The other thing to notice about this is the negative sign. And why? Why the negative sign? Well, if you remember from our initial situation there, Landon was pushed forward, so his velocity is in the positive direction. But the gas is all being pushed backwards, and so of course backwards, that's our negative direction. All right, I hope you enjoyed this lesson on Landon the Rocket Man.